was not that fun. Made for you. So thank you everyone again for being here after the day yesterday. Today might be even tougher. Let's see. It depends on also good afternoon now. I'll structure the tutorial in the morning in two parts. One before the coffee break, one after. So I remember when I was giving the title, I gave the title of this tutorial of effective and efficient thread filtering. This is quite empty words. Absolutely everything or nothing, depends how you see it. The purpose, just to set more the expectations for today, is to grow from the very nice work that Dennis in the morning did, and also Petar, part of yesterday in introducing state space models and particle filters. There will be redundancy here, just to let again the notation refresh for many of you, because if it's the first time you're seeing filtering algorithms, it's not going to hurt transmitting here similar things second, third, and even more times, but hopefully it will contain a slightly different approach, and then from that we will grow. Okay, so as I was saying, two parts. In the first part, we are going to talk about Kalman filtering, space-based models that are linear and out. And then after the coffee, we will talk about particle filtering. So space-based models that are non-linear, non-Gaussian, etc. For more particle filtering. Very clear, at least as expectations. Sometimes there will be maybe some more maybe notation or something like this, but the goal is that you don't get lost in the details or the small many equations, but rather that we keep a high level filter of what we are trying to attempt or why we are doing something. I was hesitating when preparing the slides if keeping it very simple or putting so many equations and so on. Finally, I go in a hybrid approach in the sense that the slides sometimes can be a bit scary because they contain a lot of information. I'm here to try to not go into all the details. Then you're going to have the slides. I don't know if you received already the email. Maybe send the slides to Sarah. You should have the slides as yesterday, and then you can work always in the future if your research appears relevant. Or you need it. Please work with your research, then you will have it. Okay. So I will start with this part. There are going to be a lot of basics about Kalman filtering, and then some part of research done with some collaborators, including Emilicius Nu is France in optimization, one of my main collaborators, and also Ben Cox, who you know also is part of this research. So thank you to both of them. So you are familiar already with the structure of the state space model. You saw this yesterday several times. I'm not going to tell you much about the latent state. You know what it is. It's something we don't observe in the practical scenarios. There are many ways you can see about this. I like to think of ways of a dynamical system that evolves over time. Dynamical because we have a temporal model, discrete time, and it's a system in the sense that you can put here, you can model here inside whatever you want. Sometimes you can give interpretation to this, and there were, for example, a nice example with position and velocity that Danny was talking about. That's very clear. That's the system that you would like to know more about, but you don't. Then you have some sequential, noisy, partial observations, and then you want to do inference over this system. You want to know more about it. And the magic about this, and when you start working on this, is that even if the observations are very, very, very bad, very partial, just one of the one dimension out of many, noisy, and so on, the fact that you keep observing over and over, and that you have some prior knowledge about the dynamics of the system can allow you to make a very good inference, even if the observations look very bad, I insist. Okay. And an intuition would be that if you're tracking a person, you know that from t-1 to t in a discrete time, let's say 1 second, cannot do jumps very far away in space. So this, which seems kind of innocent knowledge, of course, yes, but once you include it in your model, which is part of the transition model, then this is going to make you a powerful model and powerful predictive algorithms or filtering algorithms to estimate the position. Again, I'm trying to give you some high-level picture because the equations don't tell the whole story, but working with equations, looking at them in different angles, that gives you this view. So the state space models can be expressed in these three equations. I agree with Dennis that at the end of the day, what matters is the third one and the second one. Third one is just the prior knowledge of the initial state. Sometimes even we can consider to be known if you know what the version, for example, start or something like this. So sometimes, similar as Dennis, sometimes I omit X naught or the prior of X naught. And what matters really is in the long run, it's how the system evolves from t minus 1 to t, and how the observations you have relate to what we want to know about the state of this system, which is the latent state. Okay? So those are the dimensions here. I think in the second part I will use dx, but nx, dx is the dimension of the latent state, and this is the observation. Again, if you have any question at any time, just interrupt me. Don't wait until the end. We saw the standard problems yesterday. Peter had also a very similar slide like this. We observed this data, these observations. That's the notation, but I think now you're already familiar with. And then your goal is to do tasks like this. You want to estimate the latent state given all the observations you have until this moment. So you're not allowed to see future observations in this case, but in other scenarios, you may be like, sorry for jumping here in the smoothing, you would be able to see future observations given an estimated past state, okay, with tau being greater than 1. You may want to estimate also this joint distribution. We are going to see that estimating this, you can see this as a marginal, right, distribution of this joint distribution. The two tasks of inferring these two distributions is very related, and this is called sometimes the joint distribution, sometimes call it the smoothing distribution, which is somehow confusing with this one. Okay, this one you can also compute it by departing from this and marginalizing all the dimensions that you're not interested about. Anyways, what matters is not the names, and also I wanted to now that I have the opportunity to have your attention, and if many of you are starting in this field, if you go to some authors, they will call it slightly different than others. And not to say if you go to stats preferences, applied probability references, signal processing references, machine learning, and so on. So just be prepared that even the same topic is going to be presented slightly different or sometimes very different. Yes, so not scary. Something I didn't comment yet is the model parameters. I'm going to denote them here as theta. We will see later for the linear Gaussian model, but those parameters parameterize, they tell you more about these equations going sorry of the transition model and the observation model, right? In general, when you do filtering, you assume these parameters to be known, but we are going to enter into this very, very soon. So this is the Bayesian filtering approach in the joint distribution. So this is the naive version where you would have a Gaussian, sorry, not Gaussian, a joint distribution here. Then this is the posterior, this is the likelihood, the prior, and this is the marginal likelihood. In this case, well, I'm not representing here theta, but just showing you a very simple setup. Remember that, as Dennis said yesterday, every time you see P of some Y's, this is a number, because Y's, you are going to observe them. So it's just, you plug them in some PDF, and then you obtain a scalar. It is possible to do Bayesian inference in this way. The thing is that in most scenarios, you are going to either work online, and then you're going to keep receiving observations, or still, even if you have stored all your observations, you would like to process them in some specific way. I'm not going to enter into the details, but you can see that the more observations you have, this object here has more and more dimensions. And I think everyone knows in this room that doing inference in high dimension is a challenge. Also, we would like to save our efforts in the sense that if we did some inference up to some time t, then if we receive a new observation, sorry, we don't want to recompute the joint again, reprocessing all past observations. So we would like to do conditioned in sequential Bayesian inference, and this is what the standard filters do. They process one observation at a time. So the typical scheme is we want to go from t-1 to t. We saw it yesterday. This is the filtering distribution at time t-1. This is the filtering distribution at time t. Hopefully the colors helped someone, just because otherwise it's maybe a bit dry. But the goal is, okay, if I go to here, we can do this in two steps. One step is to the prediction step, in which we are going to condition still in the same observations as in the filtering distribution of time t-1, but I'm going to use my knowledge of how the system evolves, and I will compute this predictive distribution of the state. And once I have it, in the update state, I will use the observation, but note that only the new observation appears here. The past observations were already acquired. The information was already incorporated in this guy here. You do Bayes rule, and then you obtain the filtering distribution. Just 2 steps each time, every time you receive a new observation, okay? And then maybe you're interested in moments in integers with respect to this filtering distribution as Dennis presented yesterday. So this is just another way to express an integral, which is with respect to this filtering distribution, and this is the moment. For example, if you want the mean, then it would be just this, okay? So let's go even simpler, and let's particularize these general state space models in the case of linear Gaussian. I don't know if it was exactly your notation, but very similar, if not. Linear Gaussian in our context is going to be simply this model. I say in our context because in control theory, you may encounter here an extra signal that is related to a control signal that the user can turn. Here, we are not talking about control theory. But anyways, the linearity you see it here because the new state depends linearly through this linear operator from the previous state, okay? And then we are going to add some additive, as we added, this additive Gaussian noise, which is independent from any t, different t, and also is going to be independent from this other noise that is here in the observation process, which on top of this, again, additive and Gaussian noise, is going to have the linear mapping between the latent state and the observation, okay? So this you can see that this maps the previous diagram that we saw. By the way, I don't know if everyone is knowledgeable about these probabilistic models. I think probably Dennis, you assumed yesterday that everyone is. I assume also that everyone is, but if not, just take a look to probabilistic models and Bayesian networks, because it's quite useful if you're going to do your own derivations or to understand the derivations of the filters, to understand the conditional independence or certain variables, given that you observed some other variables and so on. All these rules, it's nothing very, very fancy, right? But quite useful or necessary to understand. So for example, here, the fact that the model is this way means that even if you observed, if you had access to xt minus 2, minus 3, minus 4, and so on, given that we have this Markovian structure, conditioning on t minus 1, you have all the information you need. So previous states are not going to give you extra information. This is what I'm talking about. Okay. So just also to reinforce the idea of the linear Gaussian state space model, note that you can express it in this way or you can express it in this way, and both equations or both models are exactly the same. This is a probabilistic notation. This is a more functional notation. Again, different part of the literature will show you different ways, but it's useful to think both ways. Sometimes it's useful to think one, sometimes the other one. For example, if you're going to do the derivation of the Kalman filter, this is going to be very useful because you're going to operate with these Gaussian kernels and then you will carry on calculations to have Gaussian distributions everywhere, which is what Kalman filter does. Dennis explained it very well yesterday. So here I'm going to have just some slides that will go very fast, but just remember that the goal is to go from t-1 filtering distribution at t-1 to filtering distribution at time t. And if we start with this being Gaussian, because of the Gaussianity here and here, and because of the linear dependencies, then we will continue having filtering distributions that are Gaussian over and over again. Probably we didn't discuss much yesterday about smoothing. Today is somehow necessary in what I'm going to tell. The goal is to compute these smoothing distributions as well. Again, think of working offline. You have your sequence of observations. You want to know where the person was in the example of Dennis. But since you have all the observations that are already stored, you can think, okay, future observations, the end of your data stream, may help you and will help you to find out where this person was in time instance before the final observation. So this is what you are trying to do. You are trying to estimate the position at time ht, given all the sequence of observations. Okay, this is the equation of the smoothing distribution. And it's possible to compute it in the case of the linear Gaussian with this RTS smoother. I will not dare to try to pronounce these three names, but maybe they are German. We have them. You can tell me later. In general models, still is going to be called a smoother. We may talk about particle smoothing, which is the version, the particle filter version to smoothing of this smoother is to the Kalman filter. Okay, we will not discuss much today, but just so you know that there exist many methods around this. Okay, just a bit of history. Peter was telling already yesterday some anecdotes about Mr. Kalman. He developed the Kalman filter in the 60s. I once presented this to a Russian audience. Be careful, I don't know if there is any Russian here, because they claim, and I think they have a point, that some Russian mathematician, that I forgot the name, so apologies for that, developed it as well in the Soviet Union similar times. And you need to understand that those times in the Cold War, there were not that much communication, and actually sometimes people who know Russian can dig into the Russian literature on those times, and you can find gems, you can find very good papers just written. So many things were replicated, let's say, at the two different sides of the wall. It's also I like to tell this story to students, to PhD students. The second paper of Kalman, this one here, was rejected. So first, be prepared to be rejected. That's something useful to I think to hear, and also to normalize it. Kalman himself, his second paper, still famous paper with more than 9,000 citations, was rejected with one referee, reviewer 2 probably, saying it cannot possibly be true. Doesn't mean that they didn't add much maybe evidence why this could not be true. But anyways, it seemed to be true. Also, the Kalman filter is a very, very famous algorithm, and it has been implemented so many times in so many domains, and still works today in a field, robots and machinery in all possible fields you can imagine. And it was also in the lunar module of Apollo 11, the first craft landing the moon. So I think that's quite cool. And I had another anecdote. I didn't have the chance to see Kalman, but I met many people that were attending, even inviting Kalman in the 90s and early 2000s, and they invited him conferences to be plenary speaker, and of course to talk about Kalman filter. But he invented this in the in the 60s. So you imagine a person 40 years later, you know how it is. Even ourselves, we get bored of our papers 2 years later, and we want to talk about something different, right? And every time was like, no, please tell us about the Kalman filter. So this is like some singers, for example, like Despacito, you know this song? 10 years later, this Fonsi said, no, I have a new album. No, no, no. You're going to come here, but you're going to sing Despacito. But that's Kalman filter for Kalman himself. Dennis yesterday showed us about the Gaussian distribution properties, and maybe Peter also had it in the slides. The Gaussian distribution has very nice properties. For example, that the joint, if the joint is Gaussian, then you can have marginals that are Gaussian as well. The conditionals are going to be Gaussian. I will skip that just to show you a representation. This is a bivariate Gaussian distribution. The projections here are Gaussian. Here you are conditioning in one dimension or in the other one, and then you get Gaussian distributions. And this is what allows the Kalman filter in its probabilistic version or probabilistic derivation to keep running with these Gaussian distributions. I agree with what Petar said. It's in the Kalman himself and in other parts of the communities. The filter itself is seen as a point-wise filter for minimum mean square error estimation. You don't need to assume Gaussian distribution. What does it mean? It means that not that distributions might not be Gaussian, but still the solution, the point-wise solution may be the same, even if the noises are not Gaussian. Okay, just to keep this in mind, because there are several ways in which you can derive the Kalman filter. But the way it's derived here in these slides and also in the slides of Dennis is through the Gaussian noise distribution and then manipulating Gaussian distributions. So 2 steps, prediction and update. I will not take too much time on this. Remember from the previous filtering distribution, which is Gaussian, I'm going to obtain this 1 step ahead predictive distribution of the state. You just need to do this, you can see this convolution, then you are going to have Gaussian here, this is going to be Gaussian. There are several interpretations about this, how the mean is projected through the dynamics of the system. You can see it like this, through this matrix AT, and also how the uncertainty, for example, here can be contracted, for example, if the dynamics this matrix has certain properties. I will not elaborate on this. But also remember that there is a noise in the state. Well, here you see the inflation of the uncertainty because of this noise. The more noise you have, the more noise you will have here in the predictive. That means that I knew, for example, very well where the person was at time t-1, given all the observations at t-1. But time has passed between t-1 and t. If this person is very hectic, then a lot of noise in the transition model t-1 to t, meaning that now you have a lot of uncertainty of time t. Then in the update step in time t, you will see that the covariance here is going to be, should be covariance for some people call variance, even if it's in higher dimension, but anyways. You can see that depending on how much you trust your observations, you may contract again the uncertainty. Yes, now that I observed the new observation, the new data point at yt, at time t, then my covariance will be shrinked. Yeah, I'm trying to give you something complementary, because for the mean, I also agreed with what Dennis and Petar said yesterday. You can see this equation here. This is the predictive mean, and then this is the Kalman gain. This is a prediction of the observation. If your prediction is good, you don't learn anything. But if your prediction based on past observations without seeing the new observation is not very good, you will use this gain in order to move into a better position of the state, given that you have new observation. Okay, just again, different perspectives or a bit more context. Obviously, the equations are the same, and the equations are summarized here. So this in the left, you have the Kalman filter. You saw the equations yesterday a couple of times, and then in the right, you have the RTS smoother. Remember the algorithm that will help you to compute, in the case of doing the job exactly, the sequence of distributions, PDFs here, which are Gaussian with this mean and this covariance. So what you need to see here, without entering into the details, is that at each time step, you will have a new observation, right? You want to process it. And something you can realize here is that the observation, or the only time an observation appears here is only in this step and only YT. So you could discard, throw away all the past observations. You don't need them because you already processed them, okay? And all this information is present in the mean of the previous time step. Actually, something you could observe as well is that the observations never affect the covariances, but that's something that if you realize of the dependencies, Z here is going to appear only here, which goes here, and this goes here in the next time step and so on. It does not go into the loop, let's say, of the covariance adaptation. That's a side comment. If you don't get that, or you don't see why this is important, it's not crucial, but it has some consequences. Then what you do at each time step is to do these 7 equations, and then you go from the mean and covariance of the filtering distribution T-1 to the new mean and covariance. This is the high-level perspective. Without understanding any detail, you observe a new observation, you incorporate it, and you go from this tube to this tube, okay? Now you say, okay, at time t equals 7, I did my filtering distribution, and I know the mean and the covariance. And let's say that your whole sequence of observations has dimension 100. Then you want to say, okay, but I would like, I'm working offline, and I would like to incorporate future observations, future information, time 8, 9, so on, and to 100, to refine, to have a better sense of where this person was at time 7. How can I do this? Well, wait until you process all the observations. Now you're going to have the whole sequence of Kalman solutions, the filtering distributions, and then you can run your smoother. Something to at least to have in mind or to remember is that the smoother is going to run backwards. And how can you interpret it besides all these equations? Again, we are not going to enter into the detail of every equation, but the high-level picture would be, look, at each time step, you are going to start with the mean and covariance that already, of the filtering distribution, that already contain a lot of information about where this person was at time ever. And I'm going to refine it. You can see it as a refinement in which, okay, you create these 2 variables here, and then these 2 variables here. But what matters is that you go from the filtering distribution at time t, covariance at time t, to the same object, but now it's with the S, meaning the smoother. So while this and this was where the person is with the uncertainty at time t, given observations up to time t, now these 2 are conditioned, or this one and this one are the covariances of this distribution that is conditioned also on the future. Does it make sense? You use the information of future observations to refine the filtering solution, and now you modify it based on how informative, extra informative the new observations are about your known, which is estimate where this person was, hidden state, time 7 in my example. Make sense? Okay. So in 2 passes, forward and backward, then you get. Note that here the observation does not appear. Again, let's not enter into all the details, but you don't see YT here, okay? Otherwise I would have put it in green. So you could have already, yeah.
But you need all the means and covariance matrix from the previous steps. Or...
Correct. Yeah, correct. So you need to store all the means and all the covariances here in order to reuse them here.
But wouldn't you think that the observation is like, to store the observation would be less memory?
So you're right. You are totally right. Might be a less memory, but then you would still need to reprocess all the observations at any time, and then maybe you would not need to reprocess to store all the intermediate means and covariances, but still you need to reprocess everything. So there is, you gain something, maybe you lose the fact that you need to store this. Note that also that you were trying to estimate those things. So you are storing them because in some sense you want to keep them. If you're doing the smoothing distribution, it's because you care about the position. A different thing is when you're doing just filtering online, then what you care is where is this person now? I don't care about where it was some time ago because I'm doing, I don't know, Google Maps and I'm trying to help this person to reach some location. Then I want to know where the blue point is. That's all I care. But yeah.
I got a question.
This is probably just an introduction covering mostly of what was said yesterday. Thing is that all the time we have assumed that we know the model parameter. Remember, I denote them at the beginning very generically as theta. But what is theta here? What do you need? I remember once with the students, they were master students, and say, okay, let's implement the Kalman filter, and they say, well, that's very easy. Give us something more. It was one student, and said, okay, well, try to implement it. There's some real data here, and then play with that. And then after some time, I was called and say, what matrix A should I plug here? Okay, it's not that easy then, right? It's very easy if you generate fictitious data as Dennis was doing yesterday. You know all the matrices that you use in order to generate the fictitious data. And then when you do the inference, then you use the same parameters that you know that were true when you generated the data. By the way, I don't know if this was clear. I think to me it was clear, but it never hurts to reinforce that whenever you have a model and you want to try even with real world data, it's very useful to start with a simplified version, which is take the model, assume that you know the model parameters, and then take data, fictitious data, where you know the ground truth. You never know the latent state, but if you generate yourself, you do, because you are doing it yourself. You generate the Markov AR process for the X's, then you generate the Y's, and then you try yourself the Kalman filter, for example, and then you can compare the solution versus the true state. Okay. Then you go to real world problems, and then you cannot know very clearly if it's true or not, and then you need to see other metrics, let's say, to see if you're fitting well the model, etc. But that's just more a general comment. Yeah.
There's a question in chat.
There's a question that I cannot see here.
That's okay. It's Bill here online.
Bill.
Can you hear me?
Yes.
A question about the smoother. Is that an optimal estimate from the smoother, like for the filtering situation?
Yeah, in this case, yes, the RTS is the optimal solution in the sense of the exact closed form solution of these guys here. Yeah, good question, because when we will go to particle filtering, there will not be an optimal smoother, and everything will be approximations. The same that filtering, particle filter is going to be an approximation of the filtering distribution. Yeah. Thank you.
Thanks.
So how to proceed in the real world scenarios whenever we don't know the model parameters. And the model parameters here are the mean and the covariance of this initial state. Again, we could consider this to be known, and little damage may be done in many applications, see all, but in many applications. But what is very relevant is this matrix is A, the matrix that encodes the dynamics of the latent state. Matrix H, that tells you how your observations are related to the latent state. And then these two covariance matrices. These four parameters that potentially they be different at each time step. If you don't know them, there is nothing you can do. You cannot run the Kalman filter without knowing this. That was my anecdote teaching this. Is not that easy if you don't know these parameters, or impossible if you don't know what to put and you don't put anything. But even if you assume them to be constant, this is still very, very challenging. There are by my experience, depending on the applications, you may consider that some of these parameters are likely to be constant. Some others might be time varying, and typically some of them you may even know them. For example, I will comment later more, but depending how you do the modeling and what the latent state means, sometimes the age is going to be straightforward. Many times it's a matrices with ones and zeros. For example, in the example yesterday, if the latent state is a two-dimensional position, two-dimensional velocity, you may consider that you are seeing a noisy version of just the position of the target. Maybe you have just a blurry version of it, depending on the type of data. Then this is going to be just a 4x2 matrix, 2x4, sorry, that maps between the four-dimensional state and the two-dimensional observation, and then it contains ones and zeros, and then the velocities, you don't observe them, you observe just the position, but plus some additive noise, for example. This is one example where H is not that complicated. Another example is R. R might be known in many scenarios, depending again on the data, but if you are measuring some physical quantities, I think it was power, right, in your example yesterday, our signal, then you have some sensors, and you have very well characterized these sensors. You know, when you see the characteristics, then you know what is the signal to noise ratio, you know the observation, or not the signal to noise ratio, but you know the variance of the power of the noise, for example. Then this R is going to be related to that. What is going to be very, very complicated in general is to characterize this A and Q in many scenarios. So let's go to the next section, which is what do we do whenever we don't know model parameters? The way I'm going to do it here is I will try to focus a bit more, and the rest of the talk before the break will be on linear Gaussian space models. But what I'm going to say now applies more generally to generic space models, not linear Gaussian, but broader family. So I'm sure there are so many different ways, way many more beyond these possibilities here. But in order to have some clarity, at least to start with some main or some of the most important approaches, I think it makes sense to talk about maximum likelihood, maximum a posteriori, and a fully Bayesian approach of the parameter. So we are going to go step by step. Okay? So you may remember that yesterday Dennis was talking about this object here. In the case of that we're dealing now with, where you don't know the model parameters, you can call this the likelihood of these model parameters. Okay. Many times when you know the model parameters, then you are not going to denote this theta here. You assume them to be known, and then there is nothing mysterious about this theta, and then you will see just the P of all y's. Then typically in those scenarios, this is called the marginal likelihood, the normalizing constant as well. Why the normalizing constant? Well, I don't know if it's here, but you can see this as the, I will try to not use much the blackboard, sorry, online people, because I think they cannot see it here. But if you are interested in this object here, then this is simply the joint divided by the object I'm talking about now. So, I'm sorry. So you have the posterior distribution of the whole trajectory, the full sequence of states, and then you have the joint here. This is easier to express. So we will see it. This is just the product of all kernels, transition kernels, the blue guys in the licensed functions, the P of y t given xt. Then if you were able to compute this marginal likelihood, then you would immediately obtain the posterior that you are interested, if you're interested in the whole trajectory, okay? So what I was saying is that if you know theta, then this is just one number, you plug it, it's one number, and it's a normalizing constant, called normalizing constant as well, because this, when you plug here the y's, let's assume that you know theta, you plug them, then this is a function of x, right? It's a non-negative function of x, but does not integrate up to 1. So it's not a density. Once you find this constant here and you divide, Now, yes, it integrates up to 1. Why? Because the quality here, this is a density, right? So necessarily this needs to integrate up to 1. So this also, you can see that is the integral of the marginal likelihood. I'll try to use more words for the online people. The marginal likelihood, the normalizing constant, is simply the integral of the numerator with respect to all the trajectory of the latent state. That's why you can find it in a different names, but the object is the object. The mathematical object is the same. Something you can always do, and this is not because of the structure of the model, but simply because of the standard factorization of any joint distribution. You can start with the marginal. I know that everything is conditional on theta, but think just on the y's. It's the marginal of y1, and then the conditional of y2 given y1, conditional of y3 given 2 and 1, and so on and so forth. Okay, and then you can do this. I insist on this because whenever you will derive your own algorithms, and then you need to do manipulations with these distributions that are related to the model, you need to distinguish very well which things are you allowed to do just because of basic probability rules, or which ones you are going to be exploiting the fact that you have a Markovian model, for example, or that the observations are conditional independent on other states given the same state, the state at the same time. Okay. So what we want to do is to maximize the likelihood of the model parameter. So you have these observations intuitively, and I think this resonates for many of you, actually for everyone, but what you want to do is to find a parameter for which the observations are likely to occur. Okay, this is a more hand-wavy way of seeing it. And then if you find, in this case, in maximum likelihood, it has its own problems, but if you find the theta that maximizes this function, then you're finding this maximum likelihood. Then it's very simple to see that maximizing this likelihood is going to be the same as minimizing the minus log. Okay. Why? Because the log is a monotonic function, and then when you do the minus, maximizing the function, same as minimizing the minus of this function. And you will see that for many reasons, again, I will not enter here, but we usually work in the log domain. There are many advantages for that, okay? And one advantage that you can see already is that this product that you have here is going to be now sum. You work with the log, and working with sums is going to be simpler. This is some notation to say that you have this phi that decomposes in these capital T terms. I will use capital T sometimes to say that's the length of your sequence of observations. Sometimes when we work more in the batch setting, we have stored our sequence. We are talking about this capital T. When we work in the online setting, we work with T plus 1, T. We work in, let's say now, infinite horizon, or we don't define the horizon, okay? Just to distinguish between these two situations. Hopefully that doesn't confuse you. Okay, so we want to minimize this function here or maximize this function there. That's the goal. Then there are many approaches in order to do this. And what you need to understand, again, this is an imprecise statement, is that this function is going to be complicated. What does it mean? It's going to be non-convex, so you cannot just find analytic, find the only maximum, for example, and then just transform solution. That's not going to happen. Okay? Even in the linear Gaussian system, that's not going to happen, which is what is going to motivate the rest of the discussion in this debate. So you need to resort to some numerical approaches, some numerical algorithms that will approximately find this maximum, this theta for which this likelihood of the particles is maximum. And I would say that mostly there are these two approaches. Again, there are always many other ways to see things, but I think this encompasses most of the literature, which is you go to gradient-based methods, or you go to EM algorithm. The gradient-based methods, you can imagine how they are going to operate. You are going to find the gradients in the domain of theta, and then try to move into areas where the likelihood is higher. then there are these two options. One option is to simply take the gradient of the energy function, so the previous slide. This is called sensitivity equations. You can see this reference here, and also the book that Dennis yesterday mentioned, the Simos-Arca book, where I think they are explicit, the sensitivity equations. Here in this book, in this paper, you will find the gradients for the linear Gaussian in closed form. You will see how complicated it gets, even for the simplest scenario you can think of. And then you have this option B, still a gradient-based method based on the Fisher identity. I've never worked myself on doing research with the Fisher identity, and I was looking at it recently, and no matter how much I try to avoid Dennis, I found his blog to be very informative and very nice about Fisher identity. So if you want to read a bit more about this vision from gradient-based methods using the Fisher identity, I don't know if you keep writing in this blog, but
latest 2020, I think.
okay, you should write more, because we got referring to not only the post but the blog of Dennis. Okay, this is a gradient-based. Are gradient-based methods magically solved? Are they going to magically solve your problem? And the answer is no. It doesn't mean that the alternative magically will give you something, but gradient-based methods have their own problems. For example, when you have a gradient-based method, you need to adjust the step size, which is very difficult to do in general, and is very difficult to do in the context of state-space models. You can encounter also some numerical instability, so that's more a numerical implementation problem. Yeah.
Quick question, is equation 6 in closed form for the linear Gaussian system? Or
I think it should be in closed form. Dennis, you are the Fisher.
sure, I was thinking.
The thing is that this is going to be in closed form, so this is a Gaussian. So it depends. I don't know, but it depends on how this gradient. I think since this is all product of Gaussian kernels, and then you will have this derivative. It depends on how the functions are going to look. For example, if you have polynomials, then it will be, because then it would be moments of known moments of the Gaussian distribution. If you start having a more complicated function, maybe you need to integrate more complicated functions with respect to a Gaussian, and maybe not. My first impulse was that maybe yes, because we will see that in the EM that something very similar appears. We have integrals with respect to the smoothing distribution, but in the other case, the functions are actually integrable in a closed form. But I cannot say 100%.
So equation 6 is the gradient of the log margin lactant.
Yeah.
It's the same. So I think in the state space model you can compute it.
Yeah.
I think.
Probably yes, but no. Let's look at it later. Yeah. So the alternative to gradient-based methods is the EM algorithm. Just to poll, how many of you have not only heard but studied or seen EM algorithms? Okay, I would say maybe 60% or so. So it's a good balance. Then hopefully, still, if you heard or even used the EM algorithm, you will see it. You will see something useful. If not, let me start with this slide. I took this from this reference. I think I had the reference somewhere, but anyways, the idea is the following: you are trying to maximize this function, and this is a very simplified problem in the sense that here theta is of one dimension. In our example, in general, we may have dozens or even hundreds of dimensions to be learned to be of theta is going to live in this space, and then you're going to work in this very high dimensional space. But here theta is all of one dimension. Let's assume that this is the function that we want to find the maximum, so likelihood of the parameters, and then we would like to love to find this point. This is what we are looking for, this point here, right? You can see my pointer, right? Then the way you can start thinking about EM is that, look, if I have a very complicated problem, and it's complicated because this function is nasty, is it possible that I split it into a sequence of easier problems for which I know the solution of these easier problems? This is the first thing that I put in your head if you never heard about EM algorithm. Split a very complicated problem into a sequence of easier problems. Okay, let's look a bit more into the details of what we mean by an easier problem. Let's start here. We have this function, and this function is an easier problem. You can think of this as being a parabola. It's a quadratic function, and for any quadratic function, you know it's a maximum, right? Then this is a function that you wish you had, because you would know how to maximize it, right? Then, okay, the way that this function is built is has two properties, at least in this slide, but in general, you will see that, okay, it's quite accurate, which is first, at this point, this function is tangent to this function, to the true function I want to maximize. So yes, it's true that my also called surrogate function, the easy one, is not the same as the other one, but it has something in common, at least in this point, right? It looks alike a bit in this point. Okay, I'm trying to fool myself. They don't look alike, I know. The second thing that the second property this function has is that everywhere in the whole space, the function is below the true function. Okay, this you agree with me, right? Okay. The way EM algorithm is going to proceed is the following. You start with this approximation, good or bad, but it's an approximation. Then you say, okay, I don't know the solution of the whole problem, but I know the solution if the problem was this one, which is the maximum here, right? So my new estimate is going to be this one. Here, sorry for the notation. Here you could see it as I plus 1, so the iteration index, okay? It's not T. Then this is my new estimate. Okay, what you don't see here is what's going to happen in the next iteration. In the next iteration, I'm going to proceed the same. I'm going to find another surrogate function, which is going to be also tangent to this point. And I need to find a function that still follows the second property, that is always below the true function I'm trying to optimize. If you imagine this, then you have something like this, and then the maximum would be around here. And then that would be your next estimate. Then you would find another surrogate and so on. And then eventually, with this initialization, you would find this point. Does it make sense? Or particularly for those who never saw EM?
No, just a question.
Yeah.
Just in general terms, how do you find that quadratic, or how do you know it's below the function?
Very good question. It's problem dependent. And we are going to see for the linear Gaussian very soon, because we are going to see it, the EM for the linear Gaussian, that is possible to have it. We are not going to have the equations here, or that why you have the surrogate function to be a minorizing function, which is the name for the true likelihood that we try to optimize. But it can be proven. In other scenarios, would be more difficult to prove, and it's one of the keys of the but very good question. Yeah. And another key point, now that we have this nice plot that I took from Mr. Bernstein, is that you can see that if we did not initialize here, but for example, we initialized in this point here, probably, very likely, we would start having surrogate functions. And then if this is a local maximum, which I think it is, it's slightly above this small valley here, then we would get stuck there. So another thing to remember, and maybe hopefully it helps, is that the EM algorithm is not going to guarantee that you find the maximum, the global maximum of your function. You could get stuck in a local maximum. Yeah.
What is the added benefit of this compared to gradient descent? That essentially you also do a gradient descent step here plus some.
You're a very good question. Technically, you're not doing a gradient, even though you can see the going in the direction of the gradient, but you're not completing the gradient. So
That's
here-
how that the surrogate function has to have the same tangent line compared to, did I understand you?
Yeah, in this case, yes, but not necessarily you need to find the gradient in a closed form solution. So it's not that you need to do it and then find the gradient about this point and so on. You need to find a function that shares in this case, it would be the derivative here, but you don't need to analytically find the gradient. Yeah. What is the advantage? Well, that you don't need to find the closed form solution of the gradients, and also then in many scenarios is going to converge faster, and it's going to have less. For example, you don't need to have a step size either of the gradient. Yeah. We will see very soon. We will see what you need. For example, for the linear Gaussian, you will see that the gradient is not present there. But I understand that it looks you may need it.
I'm sorry. But couldn't we argue that like the choice of the step size in this case is a bit like choosing a function that is always under the overlying.
Exactly. You instead of having the complication of the gradient and having the step size, you need to find this function that is going to be minorizing. Then you are trading one thing by the other. Yeah. I'm not claiming EM is better in general than gradient descent. Not at all. It's true that in the state space model community, most of the algorithms use EM, and there are many reasons, some of them I said, and then it could enter to be quite technical about why EM is going to work better than gradient descent, but in general, there is no superiority of one approach over the other. And then you will find many models in which communities heavily EM, but many others where it's gradient based. Yeah.
So does it mean you can use EM for a problem where you cannot take the gradient because like it's not differentiable, or?
I think so, but yes, as Hugo was saying, you need to be able to find these functions. So we're going to see very soon about how to not how to find this function for every problem and so on, but how to frame the whole EM, how to find it for the case of Gaussian, and then we can elaborate for other models, but we don't have time. Yeah, very good question, everyone. So this is the EM algorithm. It was introduced in this reference here, et al. And the EM algorithm has been applied, as I said, heavily to state space models, and particularly to the linear Gaussian state space models. There are some nice properties that we can see later. Its finding is based on, and this generalizes the intuition I gave you in the previous slide. It generalizes this equation for general for any dimension of theta. The function, the surrogate function, sorry, the true function we try to maximize is this one. It's going to be the surrogate function. It's going to be a genetic function that depends on density of the whole trajectory here in some parameters. Okay. So for the moment, I'm not telling you much about this, because what does it mean that this function depends on you can see this as some arbitrary density. Well, you can express, and this is related to, you're familiar with variational inference, is quite related to the elbow. You can see this very similar, if not the same. And then you have here, this coming from a Kyle divergence, by the way, but again, I don't want to drop names as I said yesterday, but just if something resonates, it's good to always to attach it to something, some knowledge that you have already, just to build some intuitions. Then yeah, this function here is going to be the product of Q and the log of the ratio between the joint of states and observations, and this appears again, the Q here. So remember that this is any arbitrary Q, okay? it doesn't mean that any Q will give you any F here. It tells you that for any Q, this equality is valid. That any part of the space on theta, you will have that your function, your surrogate function is below the true function you try to minimize, okay? Then the approach here is we want to maximize this, but what we are going to do is we're trying to maximize the minorizing function, okay? Which is related to minimizing the minus log likelihood and minimizing also this one. But we are going to work now in the maximizing setup. Then what's the goal here? Well, I want to remember that this inequality is valid for any Q, but again, it doesn't mean that all the Qs are equally good. You can imagine some minorizing function being very loose, very different from the true function you would try to minimize. Ideally, you would like to find minorizing functions that are very similar to the true function you try to optimize, and then optimize there, because if you optimize in the surrogate that looks alike to the problem, then you're solving the problem better, you're approximating better the problem. That's the intuition, okay? So we have these two elements, which is, one is this function Q, for which I insist this function still is going to be a minorizing function. And then you will try to improve this Q in such a way, I insist, that your surrogate function is closer to the true likelihood. And then this is the E step, and in the M step, you will find the theta that minimizes the function itself, okay? As we saw before, once you have the surrogate function, what is the optimum of this surrogate function? Hopefully this will help me in the next iteration with the new theta I minus 1 to build a yet better surrogate function. Does it make sense? The mechanism that doesn't matter all the details, but at least improve the function, optimize the function. Now with this new estimate, get a better surrogate and then optimize it and so on. Well, it is possible to show that in this case, the E step, the function that maximizes this is going to be, and remember, we are doing optimization over a function space, so that's getting a bit technical and a bit complicated. But just bear with me that in our problem for our model, the function that maximizes this quantity here is going to be the smoothing distribution. And that's going to be a great advantage we're going to see very soon. Why? Because now our function f here, if we are going to plug as q, remember that this was q here appearing here. What we are doing here is we are plugging the q at time I, at iteration I will plug the smoothing distribution. I will plug it here, I will plug it here. Then the log, you can do this, the log of this minus the log of this. This is just what you're seeing here. And the thing you need to realize from this decomposition is that now there is this function. So now the whole function, when you plug the smoothing distribution as this q, decomposes in this part and this part. In this part, theta does not appear. Why not? Because you need to distinguish between a theta and a value of theta that I plugged coming from the previous. Okay? I'm going back again, sorry. You are going to come here. You are going to find this theta I, and then you will plug it into the next step. But when you come here to the next step, you want this, by the way, this is a type 1, that doesn't help. This is a type of, this should not be here. Then, oh, sorry. Then, stay with me, this is correct. When you have this function that depends on two things, one function and the parameter theta. The function originally would have depended on theta, but we plugged the theta in order to run the smoother. Remember that in order to find Kalman, to run Kalman and the smoother, any filter and any smoother, we need to set some parameters, right? So in order to find this smoothing distribution, we need to plug some parameters. We plugged it, then the function itself does not depend anymore on the parameters. You plug them already. It's not a function with respect to theta. What is a function with respect to theta is this one. This is just a functional form, and then it has a variable that has not been, let's say, resolved. It's not been, you have not plugged anything. So this depends on theta. This depends on theta, but this doesn't depend on theta. What's the point here? The point is that if I want to maximize this one now with respect to theta, this part still depends on theta, but this part does not depend on theta. So I'm going to call just the part that depends on theta, I call it calligraphic Q. And you can see that it depends on theta, but we plug this theta I minus 1. This is what I meant. This is a function with respect to theta. Theta I minus 1, I plug it in the past, doesn't matter. Now, this is just a function where the input, this of freedom, depends on the theta itself. Does it make sense a bit? Yeah.
Wasn't the smoother run after you run like the Kalman filter, right? So the smoother had all the parameters from the Kalman filter.
Yeah, that's
The
correct.
Kalman filter needs like start at theta 0. Did you have to run the Kalman filter and the smoother?
Totally correct. Totally correct. And we're going to see it very soon for the linear Gaussian state space model. But in order to obtain this smoothing distribution, which by the way, this is the joint distribution, but not only the smoothing at any time t, but of the whole trajectory, you need to run the whole Kalman, the whole smoother. Both you did it with this plugin, this estimate, previous estimate, and then you use this in order to compute this function. Okay, and the function is a function of theta. And then once you have it in the M step, you take this function and then you maximize with respect to theta. And then you will use this new estimate to run a filter, to run a smoother, to compute a new function Q, to optimize and obtain the new theta, so on and so forth. This is the algorithm. Yeah.
So then how would you do it like online? If you had like
Very good question. You cannot do it online. Fantastic. Yeah. There are EM online versions of EM, but it's going to resort of approximations, window size, and but you need to do it offline. Yeah. Because you need to test how well your new parameter guess, which is theta I, works, how compatible it is with all the observations. You could do in mini batches, you could do in mini, there are many attempts of doing it. None of them probably are very successful that I know. Yeah.
I didn't catch why is this choice of Q identical or meaningful?
The sense of the different Q you choose here is going to determine how tight, how well, how good approximation this function is going to be. So you may have a, if let's say that the Q being the smoothing distribution gives you the best possible, in some sense, surrogate approximation here. You may find other Qs that still will give you a minorizing function, but that might be a very loose, very bad approximation of the true function.
I mean, like it sounds equal, but can you it's like the maximizing function for this? Or what?
It's you can see, for example, for this kind of models, you can see the proof here that this is the maximized.
That's not directly obvious.
Absolutely not. You are totally fine. If you don't see it obviously, it's totally fine because it's not obvious at all from here. It's not set, it's just referenced. This is the optimum or the optimal function that you can plug into the whole framework.
The reason that this form of F works is just a convexity argument.
What do you mean by that?
So it's a minorizing function because that integral is a convexity argument.
Well, I'm not sure if you need it's
F lies below this function that you
again, it's related to the other question. You cannot see it from here why this is a minorizing function, even why it's the best function that applies here. Yeah.
I'm not saying it's best. I'm just saying that it's minorizing because of a convexity argument, because you're summing. Is that the argument? You're summing.
I don't think it's the only argument, because this the true function is not convex. So would imagine this function suddenly doing something very abrupt here, even if you have a convex function here, still would not be a minorizing function. So it's more complex than this. Yeah, but it's a very good, both very good questions. But every question you had is very good, and I'm very happy that everyone is so engaged. But it's
online
it's-
as well.
what?
You have a question online as well.
Okay. Anyone online?
Yeah, I'm just waiting. So just a practical question. You haven't said anything about how much data you've got or how many points you got. Presumably, if you're trying to apply this and you haven't got enough data points, it's not going to work. And what would happen?
Well, good question. I'm not sure what you mean, but it's not going to work, because it's like this sentence of unhappy families are happy in their own way, of Anna Karenina. So there are many ways in which this could not work. One could be because you have not enough observations, and then you have tons of parameters. Then you have even an undetermined, even if you wanted to do something very naive. Not to say that you have noisy observations, it's impossible for this to work. But you have another problem, is that if you have tons of observations, then the likelihood is going to be super picky, and then even for EM, this is going to be a problem to find the best parameters. There are many ways in which this could not work. I didn't go into practical details, because even the theoretical details, I'm still saving a lot, and still it's tricky to discuss. But of course, very good question. What would happen if you don't have enough data? I'll tell you something that is also related to some comment of Petar yesterday, which is we have priors in order to help for that. In many scenarios, these thetas are going to be interpretable. They have a physical meaning, and then if you know what you expect, which range of values, then you should not do maximum likelihood. You should do the second point of the list I presented, which is maximum a posteriori. That's good news. Anything you learn about maximum likelihood, either in gradient-based methods or in EM-based methods, it's very easy to adapt them, to include the prior, and then to have a maximum a posteriori versions of both EM and gradient. Yeah, hopefully that responds. So I was here. Yeah, I think we have a bit less than 15 minutes, so I will try to not present everything, but to give you, we're arriving to the end of the most essential part of this slide. So I'm satisfied with that. We were here. We are already happy computing this function Q, and then in the M step finding the maximizer of the function. Let me tell you that also this function is not necessarily convex. In the example before, it was convex. In other examples, might be not convex, or in other examples might be still convex but complicated. I mean, not straightforward. Not don't think of a.
I was not saying that this function is convex. I was saying that this integral that you have, form of f, it's log of something divided by something. So you're basically summing up some logs. Is that why the f lies below?
Okay. I see the argument. Yeah, possibly yes. It's that's related, but that's related to the derivation of the KL divergence minimization and how this elbow-like thing appears. So yeah, let's maybe we can discuss.
Integrating with some sort of Q is some sort of PDF. So basically, you have a convex combination. The integral looks like a convex combination.
I'm not sure what you mean now, but by a convex combination, it depends on the how you factorize this. Maybe let's discuss later, because we don't have maybe in the break we continue the conversation. So you have this function Q here that you try to maximize. Once again, this is going to be the smoothing distribution at the previous, even the previous parameter. And here you have the joint, maybe related to what you were saying, that factorizes very, very nicely. It's just the concatenation, the product of all transition kernels here and all the observation kernels here. Then we would like to have this in a closed form. The linear Gaussian is going to be in a closed form. And then in the M step, what we need is to find the maximizer. Okay, you can see that's finding the point for which this is 0. Is maybe in some cases there's going to be more than one solution, etc. But I will not enter into these more complicated cases. What I'm going to do is to go to simpler case, which is the linear Gaussian state space model. And because of the this smoothing distribution is Gaussian, then this is the function you obtain. And now I'm giving you this very ugly, very big equation, not to overwhelm you, but just to have a picture of how this function looks like. You can find more of this things in the Simus Arca book that Dennis was mentioning yesterday. The thing you need to see here is that we go back to see our parameters that we were interested about. So here we are considering both all parameters to be constant. You have P0 here, remember M0 related to the initial state, and then you have the transition matrix A, the observation matrix H, and the two covariant matrices R and Q, observation and the state noise. Then you have these matrices that are going to be available. And what I mean by this is that if you see all these elements here, those are just depending on either the observations or these M and P smoothing mean and covariance elements. So once again, you're going to come here. You run the Kalman filter and smoother, as you were saying with the previous theta I-1. Then as byproducts, you're going to obtain a lot of quantities of interest. For example, the means and the covariances of the smoothing distribution. Okay. Then with this, imagine this sigma here, you will construct these matrices here. And with these matrices, you will plug them here. And once you plug them here, everything is a function of theta, theta being all the model parameters. Okay. Now you completed the E step. In the M step, you need to optimize this with respect to what? With respect to the theta parameters, okay? Not easy, but at least close form solution of function Q. So once again, I'm presenting the EM over and over, but now every time a bit more simplified. Now in the E step for linear Gaussian state space model, we will obtain a closed form solution of this function here, and then we will compute the maximizer. Finding the maximizer of the whole function here might be not straightforward. I will not have time to discuss about this, but just think of a next scenario where you know all the model parameters for whatever reason. So you are able to come here and say, look, I already know this model, the ground truth of the P naught, of H, of Q, and R, and so on, except A. I don't know A. I want to estimate the model parameter A, which is very relevant and very complicated. Then the whole function, very ugly function I show you, is going to be now this one. It's a simplified version because the other parameters, I know them already, right? So in this case, I would like to do maximum likelihood of parameter A, the linear Gaussian state space model. Well, you need to run the EM algorithm here, and then alternate between the RTS smoother, and then here you take this function, and then you optimize. And in this case, it's a quadratic form, so you can find easily the optimizer closed form solution, and then you obtain this. It's not guaranteed. It's not always the case. Even we will see very soon. Well, I don't have much time, but I will show you very soon one example where the M step, sorry, is not closed form solution. And then we may have even a convex function here, like this one is a convex function, but instead of having a closed form solution, you need another iterative process here in order to find the maximizer of function Q. So you have an iterative process, and in the EM step, you also have a second iterative nested process to obtain the optimizer. Okay, I think that gives you hopefully a very good high-level picture of EM algorithms. The maximum a posteriori, the only one I the only thing I want to tell you before I just spend in a few minutes in something related to this EM algorithm is that, well, if you care not only about maximizing the likelihood, but maximizing the posterior, well, what you can do is to maximize the product of likelihood and prior, and that's equivalent to maximizing the posterior. Then, of course, you need some prior knowledge of theta, but as I said before, in many cases you have it. In many cases, it's even desirable to include it. And in this case, very similar to before, if you remember this function that we wanted to, in this case, minimize, was this one. This is related to all this decomposition of the likelihood. Now we have this minus log prior as well. So now we want to minimize this, which is equivalent to maximize the posterior. So finally, a third version. You remember I put these 3 bullet points. The third possibility would be to be very ambitious and say, look, if we are Bayesian in our approach to estimate the filtering distribution, that's a definition Bayesian. So we want to know probabilistically what is the sequence of hidden states. Why not being also probabilistic in theta? Okay. Then I would like to obtain the closed form solution of the posterior of theta given all the observations. Again, something you cannot do online. There are some methods, but still it's a very tough problem. So you would like to do this thing of line. You have the sequence of observations and you have the posterior, and then you would like to obtain this. Okay, you can see it like this. You could have first have a probabilistic estimation of all unknowns. What you don't know the model parameters, you don't know the latent states. What do you know? You know the observations. So you compute this joint and then you marginalize. But come on, it's already complicated in general to obtain the filtering distribution, except in maybe Kalman filter. Linear Gaussian models. This is going to be very complicated, even in linear Gaussian state space models. Okay, so later this week, fortunately, so this slide does not make justice to what is going to come next week. This week, sorry, in I don't remember which day, maybe Thursday. We are going to have Yunpeng talking about algorithms in order to estimate model parameters, both in point-wise and also probabilistic. Probably we'll have Frederick Lindsten talking more about particle MCMC methods that I'm just mentioning here, okay? So you will have a better view on this type of algorithms. And now I'm going to just close with some work that we have been doing in estimating model parameters in state space models. So what you have seen now, we have devoted some time in order to see the EM algorithm particularized for the linear Gaussian state space model. Let us imagine that we have this same problem, and the goal here is to estimate matrices A and Q. Why? It's not because it's easy, but because it's hard. I don't know if you know this JFK speech in Rice University, but anyways, that's another reference. So this is a very tough problem. I said it before. We want to estimate the model parameters that relate to the dynamics. You never see the hidden state. You don't have access to the XT. So characterizing the parameters that drive this evolution of the latent state is very hard. That's why it's an interesting problem, open problem. And any of you who are interested, very, very happy to discuss about this, because there are tons of challenges here and ways to improve. So remember, this is the latent state in the linear Gaussian state space model. We assume A and Q to be constant over time. So those are the two matrices, one matrix each. And we would like to do, and in this case, it's going to be majorization minimization methodology, which is the broader family where EM is a particular case. So we are going to have some methods that are related to EM, but not necessarily strictly EM, but anyways, those are probably details. What I'm interested here, and this is what I'm going to devote the last minutes before going to have a well-deserved coffee and break for you, is a new perception or a new vision of these two parameters that hopefully will help to do the inference. Remember, at the end of the day, we want to estimate these parameters. But something that that we have not commented maybe enough yesterday and today is that state space models are very interpretable models. You can see the dependencies among the dimensions of the latent state dependencies with the observations. When you see the Lorentz model, for example, that Dennis presented yesterday, you have a very clear vision of even the physical description that you're making. And this is something very cool and something that probably we should even put more emphasis when talking about it and also when doing research. So I'm going to give a perspective in which matrix A is going to be interpreted as a directed graph, and matrix Q is going to be interpreted as an undirected graph. And how is this possible? Or what do I mean by this? You are going to see it very clearly because it's not that complicated, but I think it's quite cool. So imagine, let's go here. You have the whole model that tells you how to go from xt minus 1 to xt, meaning matrix A encodes dependencies of the dimensions of vector at t minus 1 and how these dimensions affect the dimensions of time t, okay? And then you have some additive and Gaussian noise, but we are going to focus in this slide just about this matrix. So the matrix here is A, and I have this example. So now the latent state has just 5 dimensions, okay? Then the matrix needs to be 5 times 5. And think of this as a matrix that has many zeros. Why many zeros? Because that's going to justify the directed graph perspectives. When you see the update, so focus on this equation, just this equation. This equation is the same one, but just for a given dimension I. If you see this is a matrix multiplication. Very simple to see that the row I depends on all the elements of the previous time step vector times all the coefficients that are in row I. Right? So for example, in this case, for this matrix, the update U state at dimension 1, time t, potentially would depend on all dimensions at time t minus 1. But due to this matrix, it's going to depend only on the first coefficient, second coefficient, meaning it's going to depend only on the dimension 1 and dimension 2, t minus 1. Is it clear? Because then you have zeros multiplying the other dimensions here. So what does it mean? Well, this is where the directed graph appears. Then the dimension 1 from time t minus 1 to t depends only on itself and also depends on the other dimension 2, but doesn't depend on dimension 3 and 4. If you take any other row here, you will see that the information is encoded here. The thickness is related to the absolute value of what's the strength of this dimension at time t affecting this other dimension of t at time t, okay? So you can see a connection with Granger causality. Peter was saying yesterday, Granger causality is very useful for us to have some prediction power sense of one time series affecting another time series. So this is Granger causality, more precisely conditional Granger causality on the latent space of the signals in X, the hidden state. Okay. I want to just this slide just to show you this. This is exactly what Peter said. Be careful when you talk about Granger causality. If you talk to philosophers or some people working heavily in causality, they will tell you this is not actual causality, and you had the rooster sunrise example that is very good that I will copy from now, if you don't mind, Peter. I like it. So what is Granger causality? It's just a very mechanical, statistical, let's call it, perspective. It's just utilitarian. Is this time series helping me to predict this other time series? Yes or not? If yes, then this time series Granger causes this other one. And you can see it with this very dummy example. You have 2 time series, and then this is a simplified version of the one, but it doesn't matter. You have this model And then you say this observation depends on the previous observation of the same time series, t minus 1 to t. One model. And a second model, alternative model, is that the same observation at time t given for the time series I depends on its past, but also depends on the past of the time series j, the second. If you do a very good job in predicting this observation now using, you see, it's the same model, but now you're using the past of the other time series. In predicting this, compared to what you would do without using it, then you can say, okay, this time series j contains information that helps me to predict this time series I. Then you say that j Granger causes I. That's as simple as that, okay, in the vanilla version. So a second slide about the graphical perspective now on matrix Q. I don't know if you're familiar with this. I was 2 years ago, I was not familiar with this, and it's quite very basic, apparently, property that whenever you have a Gaussian vector random variable, and then you have a sparsity, or you interpret sparsity in the precision matrix P. So you have the covariance matrix, you take the inverse, and then this is the precision. These two statements are equivalent. So if the precision matrices have 0 in some positions, position L and N, necessarily the dimension of the vector N and the dimension of the vector L are conditionally independent given the other entries of the vector. So you have conditional independences of different dimensions of a standard Gaussian vector, and this is encoded in the precision matrix. The zeros are encoded there. So we can interpret as well that if you have zeros in the matrix, not Q but P, then you are going to you can have this vision of how conditional independent the different dimensions are. And this is a final slide that contains the 2 examples I show you, just overimposed. You see here how from t minus 1 to t, matrix A in blue, matrix A, tells you how the information flows from t minus 1 to t. Remember that we have a Markovian structure. Between t minus 1 and t, there is dependence. It doesn't mean that we have dependence between every single pair of dimensions from t minus 1 to t. Only few of them affect each other. And also you have here conditional dependence on different noise additions here, but not all of them are related necessarily. Why we think this is useful? First, it's useful because now, and I will close with this without telling you exactly what final slide telling you what is the purpose, but the purpose was to estimate A and Q. We want to estimate them, but remember those live in quite high dimension. Even if you have this example with 5 dimensions in the latent state, the matrix A is going to be 5 times 5, 25 coefficients you need to estimate. And the covariance is also 25, but you know it's symmetric, so it's less, but still you have 30 something coefficients. So imagine when you grow a bit more the dimension of the latent state, the number of coefficients when you need to do model parameter estimation is high. So looking for sparsity is a good thing. It's going to help your algorithms to work in a implicitly lower dimensional space. And also it's useful because whenever you have a sparse matrices, you're going to have interpretability. When you know, for example, your case, you know it in your 2-dimensional position and velocity, you know that the velocity at time t minus 1 affects the position as well in the same dimension, but that the position does not affect the velocity. That's matrix A. That's matrix A. In the case of Dennis, because of the physical knowledge of the problem, you knew this matrix A. Imagine now that you try to you are coming from another planet. You don't know how physical things, or maybe not planet, maybe dimension or universe. You don't know how these physical quantities interact, and then you try to learn it. Imposing sparsity will allow you to say, okay, but then velocity does not affect the position. Oh, sorry, the position does not affect velocity one time a step further. This seems quite a dummy for this example, but trust me, when you go to real world examples or other real world examples, you don't know necessarily all the complicated physical laws that are involved, and then this gives a lot of information. So remember as well, many of you will work in machine learning and so on, but if whenever you or neural networks, nothing against that, and we use them well, but whenever you can have more interpretability, this is going to help. Okay, I will not elaborate into this, just to say that we have algorithms that do EM like in order to both impose or promote sparsity, but having L1 norm, if you're familiar with lasso regression, you know what I'm talking about, trying to impose or to promote zeros, but at the same time explain the observation. So this is what maximum a posteriori is trying to fit the observations, but also to incorporate some prior knowledge. So I will stop here. Sorry for taking